This video is entitled A Comparison of Power Switching Solutions, Discrete MOSFET versus Integrated Load Switch. In this training, you will learn what a power switching solution is and how to identify a discrete MOSFET switching solution in a schematic. From there, the performance of the discrete switching solution will be analyzed from a DC and AC perspective. Then, the load switch solution will be introduced and its performance will be compared to the MOSFET solution. With that, let's begin the presentation. Power switching in general refers to connecting and disconnecting power to loads. A power switch is put in between the power supply of a system and a load, and this switch will control when the load is powered or unpowered from the power supply. There are various reasons an engineer would use power switches in their system. During system startup, if the power supply has to power all the system loads at the same time, there will be a large stress on the supply. Using power switching, these loads can be turned on one at a time so that the power supply can start up without any issue. Power switching can also be used to slow the rate at which the voltage of the power supply comes up. This will help control the amount of inrush current which is generated from charging a large load capacitance. Another reason for power switching is reduced power consumption. In a power-conscious system, such as a battery-powered application, power consumption is a critical concern. To help make the system more efficient, loads which do not need to be powered can be turned off, and power switches can be used to disconnect the load from the power supply when not in use. For processor and FPGA applications, power rail sequencing is needed for proper operation. Power switches can be used to sequence these rails and guarantee the correct startup for the system. So which markets and end equipments use power switching? Almost all of them. In personal electronics, there are many battery-powered applications, such as notebooks, tablets, and wearables, which use power switching to disable subsystems which are not being used. This reduces the power consumption of the system and increases battery life. In the industrial market, mobile point-of-sale machines use power switching to save battery life, while COM Express modules use power switching to regulate which voltage rails are being used and whether or not the system is in a standby state or not. Automotive uses power switching for power sequencing the applications processor in infotainment and cluster applications. Power switching can also be used to turn on and off the headlamps of a car. In the enterprise market, servers need power switches to control the system startup. Each server has many hard drives which must be powered. To prevent stress on the power supply, switches are used to turn on a few hard drives at a time, and this will allow the power supply to gradually turn on safely. One way to implement power switching is by using a discrete solution. These solutions use a MOSFET to switch power onto and off of a load. Many times there are several discrete components which are put around the MOSFET to help control the switching or add additional features. To find one of these solutions in a schematic, it is recommended to search for a FET which is drawn horizontally. Many times, these MOSFETs are used for a power switching application in the system. The first discrete MOSFET solution we will take a look at is the PMOS solution. A big advantage to using this solution is its simplicity. Only one component is needed. By connecting the gate of the PMOS to a GPIO, the GPIO can control whether or not the PMOS is on or off. However, this is an active low solution, meaning that the GPIO needs to be high for the switch to be off. This can be a disadvantage since system power needs to be on before power can be blocked from VIN to Vout. Another disadvantage in this solution is GPIO variation. For the best performance of this solution, the MOSFET should have a very low on resistance, or resistance from VIN to Vout when the switch is turned on. This results in the lowest voltage drop from VIN to Vout with a given load current. To minimize on resistance, the voltage difference between the source and the gate of the PMOS must be high. Therefore, the best performance for the solution is when the gate is pulled to 0 volts. If there is variation in the GPIO signal, then a digital low output can be closer to 200 or 300 millivolts, resulting in non-ideal performance for the solution. This also makes using lower voltages with the solution very difficult. Vin cannot be lower than the turn-on threshold for the MOSFET, so any voltages lower than that threshold prevent the system from being able to turn on. For the following scope shot, each trace is labeled as well as color-coded with the diagram on the right. Starting at the top, we have the voltage on the on pin, the voltage on Vin, the voltage on Vout, and the current through the FET. For this example, a 4.7 microfarad capacitance is put on Vout. The scope shot shows the on pin going from high to low, so the active low solution is going from off to on. The Vout voltage comes up as expected, but the Vin voltage is seen dipping, and the current peaks at about 2.2 amps. This is because when the switch is turned on, the voltage ramp rate is uncontrolled and comes up in nanoseconds. This fast turn-on causes the capacitor to charge very quickly, and according to the equation I is equal to C dV dt, this results in a large inrush current. In this case, it only takes 4.7 microfarads to generate over 2 amps of inrush current. As a result, the power supply cannot handle the load and must drop its voltage to compensate. This inrush current can lead to undesired system performance, such as a reset or damage to external connectors or PCB traces. This second solution adds a resistance and NMOS transistor. By controlling the gate of the NMOS transistor, the solution becomes active high, meaning that a high voltage will turn on the system and a low voltage will turn it off. Also, the NMOS will be able to pull the gate of the PMOS to a 0 volt state, which optimizes the on resistance performance of this solution. However, lower voltages are still not able to be used in this solution, and the addition of the resistor adds a leakage path for the solution when it is turned on. The lower the resistance, the higher the leakage, and the higher the resistance, the lower the leakage. From an AC perspective, not much changes. The solution is still unable to control the rate at which the output voltage comes up, and the output capacitance once again causes a large inrush current. The final PMOS solution we will be looking at adds an additional capacitor and helps with the inrush current. From a DC perspective, nothing changes. The active high solution is still optimized for on-resistance performance, and the discharge path is still present when the solution is turned on. Using this solution, the voltage ramp rate can be controlled. By increasing the capacitance tied between the gate and Vout, the rise time of the voltage can be increased, and this results in a lower inrush current. As an example, when a 47 microfarad capacitance was used, the rise time of the voltage was about 150 microseconds, and the inrush current was reduced from 2 amps to 200 milliamps. A higher capacitance would have reduced the inrush current even more. Something to keep in mind is that if the turn-on time is increased, then the turn-off time is also increased, meaning that this would not work for a solution which needs a slow turn-on and fast turn-off time. The scope shot on the left shows the solution turning on with a 3 amp load attached, and it can be seen that both the voltage and current are controlled. While this solution is able to provide a linear ramp for both voltage and current, there is one anomaly observed. Both negative voltage and current are present when the solution is first turned on. This is due to the way the capacitance is pre-charged while it is turned off. During this time, the gate of the PMOS is high and Vout is 0 volts, so the capacitor is charged to the value of Vn, as shown in the diagram. Once the solution is turned on, the gate of the PMOS goes low and the capacitance is discharged to ground through the NMOS. This discharge pulls down Vout before the solution has time to fully turn on. While a higher capacitance can help reduce inrush current, it will also cause more of a negative voltage and current for the solution. With 47 microfarads, negative 1 volt was observed on Vout. This can cause damage to the load if the input of the load is not able to handle this negative voltage. Another issue with this solution can be seen when Vn is applied for the first time. In a system, this can be a battery insertion or initial system startup. During this time, the gate is at 0 volts, and when Vn is applied, the capacitor from the gate to Vout slows the charge time of the gate of the PMOS. While the gate is still charging up, the solution is not fully turned off, and power can be seen going from Vn to Vout, even though the solution should be turned off. If the load is not supposed to be powered during system startup, then this solution cannot be used. Now that we have investigated the PMOS solutions, the NMOS solutions will be discussed. From an AC perspective, the same rules apply. A capacitance needs to be added to slow the charge of the gate so that the output voltage can be controlled. Without it, the output voltage will not be controlled and there will be a large inrush current generated. From a DC perspective, things are a bit different for the NMOS. The gate needs to be higher than Vn for the solution to be on. This means that this solution is able to switch lower input voltages without issue. To get optimal on-resistance performance, the voltage difference between Vn and the gate should be high, and in order to do that, the gate voltage needs to be much higher than Vn. Two solutions for this are shown on the left. The first solution uses a charge pump, taking the value of Vn and generating a higher voltage from it, which can be used on the gate. The second solution uses several discrete components and can be used if a higher voltage rail is present in the system. While both of these solutions can use high gate voltages to minimize on-resistance, they take up a lot of area and use a lot of components to do so. Now let's take a look at some of the discrete circuitry needed to add additional features to these discrete switching solutions. Quick output discharge, or QOD, is used to pull down the output of the switching solution when it is turned off. This guarantees that the voltage for the load is pulled down to 0 volts and that the load is completely off. To do this discretely, there are two solutions. Option 1 is to add a bleed resistance on the output, which will discharge the load when the solution is turned off. However, this will also provide a leakage path through the resistance when a solution is turned on as well. Option 2 uses an inverter and transistor, and this solution will only discharge the output through the transistor when the switch is turned off. Because of the orientation of the body diode of the MOSFET in a discrete switching solution, current is blocked from Vn to Vout. However, if Vout is greater than Vn, then current is able to flow from Vout to Vn. To implement reverse current blocking, an additional transistor must be added with its body diode facing the opposite direction. This solution will block current in both directions when off, but will double the on resistance of the switch since both MOSFETs are in series with each other. Power good is a feature which provides an active high signal when the switching solution is turned on and the output voltage is high. This signal can be used to enable downstream circuitry or act as status indication for the rest of the system. The discrete implementation of this feature uses the discrete components shown to generate the power good signal when Vout is pulled high. While this solution works, it takes many components and adds to the total solution size. The last solution which will be discussed for power switching is the load switch. This one-chip solution can be controlled using a GPIO signal on the enable pin, and both active high and low solutions exist. For a PMOS switch, the on resistance is optimized by driving the gate of the PMOS to ground, and for an NMOS switch, this same optimization is done by using an internal charge pump to generate a high voltage on the gate. On top of that, the load switch comes integrated with additional features to make the switching more stable. The only con here is design flexibility, since a discrete solution can use any MOSFET needed for the application, and there are thousands of MOSFETs to choose from. That being said, there are many load switches available, and some can even be configured to better suit a specific application. Taking a look at the load switch turn-on behavior on the left, the load switch is able to control the output voltage and current, allowing both to ramp up linearly. Compared to the PMOS solution discussed earlier, this solution does not have any negative output voltage. Some load switches even provide an adjustable rise time with an external capacitor. Comparing the inrush current with an uncontrolled discrete solution, we can see that the inrush current is much lower and is consistent throughout the output voltage ramp. Another thing to note is that when Vn is first applied to the load switch, there is no output voltage or current which passes through to the output. This was seen with the third PMOS solution due to the capacitance slowing the charge of the gate. The diagram here shows a 2-scale representation of a discrete solution on the left, compared with a load switch on the right. The discrete solution using a PMOS, NMOS, resistor, and capacitor is comparable to the load switch on the right, the TPS22965. The load switch is 77% smaller and uses less components. This means that the pick-and-place cost is reduced, and the PCB for the system can be smaller, allowing for a smaller form factor. Now let's take a look at adding additional features to the load switch solution. With the discrete solution, adding quick output discharge required an inverter and a transistor. With a load switch, quick output discharge is already integrated, implementing an internal resistance to ground the output when the device is disabled. There are also load switches which do not have quick output discharge in case the solution does not require it. To add reverse current blocking to a discrete solution, an additional MOSFET needs to be added. For a load switch with reverse current blocking, no additional components are needed. When the load switch is turned off, the switch will automatically block reverse current. The discrete implementation for power good involves several discrete components to generate the appropriate signal when Vout is high. With a load switch, an open drain PG pin is provided. By using a resistance to pull up the pin, an active high PG signal is generated. To summarize, the circuit on the left shows the discrete implementation for a power switch with quick output discharge, reverse current blocking, and power good. To implement a load switch solution with all of these features, the TPS22953 load switch with a PG resistor are all that are needed. To recap, let's go over all of the presented solutions for comparison. The first PMOS solution was simple, requiring only one component, but this solution suffered from non-ideal on-resistance performance as well as an uncontrolled turn-on, resulting in a large inrush current during switching. The second solution optimized the on-resistance performance, but added a leakage path to ground through its added resistor. It also did not fix the uncontrolled voltage ramp or inrush current issues during switching. The third solution was able to control the voltage ramp and inrush current, but added negative output voltage and did not block voltage and current when Vn was first applied to the solution. The NMOS solutions have the same AC considerations as the PMOS solutions and offer better performance with low input voltages. These solutions can be more complicated, however, due to the circuitry needed to apply a high voltage to the gate of the NMOS. The load switch offers a one-chip solution with controlled rise time, a small solution size, optimized on-resistance, and several integrated features. A few key things to remember are listed on this slide. First, power switching is used across all market sectors and various end equipments. To find a discrete power switching solution in a schematic, look for horizontal MOSFETs. Second, simple discrete solutions do not have a controlled rise time and generate a large amount of inrush current. More components can be added to control the voltage ramp rate, but this increases solution size and BOM count. Finally, Load switches can be used as a one-chip solution for power switching and provide many improvements over the discrete implementation. For more information about load switches, let's take a look at some additional resources Texas Instruments provides. Several TI designs are available to show how load switches can be used to solve real end equipment problems. This TI design creates a power delivery solution for SSDs, which showcases the features and the small size of the TPS 22954 load switch. Ship mode for wearables shows how a load switch can be used to disconnect the battery from the rest of the system while the end equipment sits on the shelf of a store. This minimizes the battery drain of the end equipment and enhances the out-of-box experience for the customer. This TI design duty cycles load switches to show how dynamically switching the load switch can result in substantial power savings for the end equipment. The TI design on the left shows how putting multiple load switches in parallel can reduce on resistance and increase current carrying capability. And the TI design on the right shows how load switches can be used for power muxing and reverse current blocking. Texas Instruments also has web bench support for several load switches, which can help model load switch parameters and performance. Finally, several application notes are available, which provide details about different load switch features and configurations. Thank you for taking the time to watch this presentation. For more information and to view all resources, please visit the Texas Instruments Load Switch homepage found at www.ti.com/loadswitch. And for any questions, feel free to post on the Load Switches and Power Path Protection E2E forum.